issue. Okay, so welcome everyone to this STAT seminar. So the seminar is organized by University of Sydney and is also part of the Statistic Across Campuses initiative. So later, if you want to watch a recording of the seminar, you can just go on the blog. Today we have Davy Paindaveine from the Université Libre de Bruxelles who's giving a talk. I don't know if you remember Davy, but about, I would say, 10 years ago or something like this, I was doing my master's in Paris, and Davy was one of the visiting professors here. So he gave me a few lectures back then. I think it was 2010 or 11, something like this. Anyway, so Davy is also a colleague of Jerry, who's in our department. And today, Davy is going to talk about testing for principal component directions and the weak identifiability. Thanks, Davy, to volunteer to give a talk that early in the morning for you.
No, thank you. Thanks for having me. Thank you to both Jerry and you. And thanks for attending late in the afternoon. Boris, I feel sorry that you had to suffer my lectures in Paris, but that's indeed a long time ago. Okay, so the topic for today is hypothesis testing for principal component analysis. And I should mention that this is joint work with my colleague Thomas Verdebout in Brussels and one of our PhD students, Julien Rémy. I'll provide the references at the end of the talk. So it's hypothesis testing indeed. So it should not be a big surprise that the outline will involve results under the null hypothesis, then results under the alternative one. So try to say something about optimality issues. So something related to hopefully maximal powers. Then discuss some extension. Okay, let me first try and motivate what I will be presenting today. So if anything is unclear or if you have questions, please do not hesitate asking also online. Okay, so this is probably a useless slide, but I wanted to have it to at least fix the notation. So our interest is in a random vector x. Throughout it will have dimension p. P will be fixed. And this is about principal component analysis. So as usual, principal components result from a projection pursuit type optimization problem, where you try and find out what is the direction, the unit vector θ1 that will maximize the projection so the variance of the projection of x. And this first principal direction is then associated with a unit vector that I will denote in the sequel as θ1. So θ1 will be the parameter of interest for the testing problem I will consider in the sequel. And the later principal components will be denoted by θ2, θ3, up to θp in the usual way. And of course, it's well known that θ1 is just the leading eigenvector of the covariance matrix of X, which I will denote as sigma. And θ2, θk are the next ones. So eigenvectors occur ordered according to the magnitude of the corresponding positive eigenvalues of sigma. And of course, in the sample version, you don't have access to sigma, then you use S as an estimate of sigma, the usual empirical covariance matrix. And this one is very well behaved in this talk because we look at the complete standard case where n will be larger than p. So this is not high-dimensional statistics where P would diverge to infinity with N. No, this is very standard case. P fixed, N will go to infinity as usual. I will even make it Gaussian to be fully standard. Okay? And then the sample eigenvalues I will denote as lambda hat, K, and corresponding sample eigenvectors as theta hat, K. Good. So far it's awfully standard. Let me try and motivate what we'll do with the following toy real data example. So here what we have is an example from a monograph on robust principal component analysis, and this is related to banknotes. You have very few of them. You have 85 banknotes that are known to be counterfeit bills actually, and you measure those 4 variables that are listed there. So the width of the banknote on each of the left and right sides, and then the size of the bottom margin and of the top margin. And so you have 4 variables on 95 individuals, 95 banknotes. You can compute the empirical covariant matrix and deduce the eigenvalues that are provided there and eigenvectors that are also listed there. And when you look at the entries, so roughly if I remember well, roughly the variables have the same scales, so that it makes sense to compare the magnitude of the entries of those eigenvectors. And so in particular, you see that the first eigenvector is essentially so the first 2 variables are not really entering this first eigenvector, and then this first eigenvector is a contrast between B and T, the size of the bottom and top margins, so that it's really the vertical location of this image on the banknotes that is quite variable there in a counterfeit bills, which kind of makes sense somehow. And then you look at, and you have a corresponding quite large eigenvalues. It's not this one, it's lambda 1. You have a quite large eigenvalue compared to the remaining ones. So far so good, I would say. And that's also what Fleury is saying in the book. Then you are tempted to go to the second one. The second one is in contrast actually an aggregation. You get the same signs there for the 2 large entries, the 2 large loadings in theta 2 hat. This is an aggregate of ln r. So this is actually measuring the vertical size of the bill, which kind of also makes sense, right? That you have in counterfeit bills more variability in sizes of the banknotes. However, you have this warning from Fleury. And Fleury is writing something like, beware, the second and third roots are quite close to each other. That is, you have this lambda 2 hat that is actually not so far from this lambda 3 hat. And Fleury says, due to that, the computation of the standard errors for, in particular, the eigenvector I was trying to interpret now, standard errors will be hazardous. So they might be large, and then maybe we cannot say anything actually about the true underlying theta 2. So what Fleury has in mind there is related to the fact that when you work out the asymptotic distribution of this theta 2 hat, you get, as usual, an asymptotically standard, not standard, but you have, as usual, an asymptotically normal distribution for this guy, with mean 0, and then with a covariance matrix, that is the one that appears there. And as you see, this covariance matrix will blow up. It will be huge if lambda 2 is close to one of the other eigenvalues. So now if you divide, because then you would essentially divide by 0 or almost 0, and then you would get essentially an infinite covariance matrix, which will result in huge confidence intervals for the entries of our eigenvector θ2. Okay, and this is what's happening there, because lambda 2 is close to lambda 3, and then confidence intervals are very wide, and then that means that you don't really learn anything about the underlying eigenvector θ2. And this is what prevents Fleury from interpreting with some confidence the entries in θ2. So this is an issue to have two eigenvalues as a conclusion in principal component analysis. So this raises the following question. So can we say something about θ2, although indeed θ3 is so close to θ2? And this is what I will call a setup involving weak identifiability. Weak identifiability is lambda 2 being close to lambda 3 make to weakly identified. And this is reasonable since in the extreme case where lambda 2 would be exactly equal to lambda 3, then of course the second principal component vector would not be identified at all. Only the plane spanning the second and third principal components would now be identified, but so in particular θ2 alone would not be identified, so that it's not even it does not even make sense to try and make inference on the direction θ2. However, here it is identified. Lambda 2 is still different from lambda 3, so θ2 is identified, but we are close to a situation where it's not identified. And so you could expect that this will have a price in terms of accuracy of your inference on θ2, and this is exactly what's happening with, in particular, those confidence intervals becoming huge. So then we'll go and consider in the sequel this generic testing problem that is there. So what we want to do is to test the null hypothesis that the first eigenvector, say, so it's not important that it's the first or second, as in Fleury, or third one. Let's just pick the first. Everything that we are doing in the sequel actually extends to the second and third and so on. So let's fix the first one, the leading eigenvector, and you want to test the null that this coincides with a given direction in RP. So it coincides with a given unit vector in RP. And so the alternative is just that you would not have this equality there. But what makes the problem challenging is indeed that lambda 1 now is close to the next eigenvalue lambda 2. So we'll very soon adopt, so this talks about asymptotic statistics, we'll very soon adopt an asymptotic scenario, say, in which then lambda 2 and lambda 1 will end up close to each other. So this lambda 1 and this lambda 2 will be regarded as function of n, and they will get close to each other as n diverges to infinity. This is the non-standard thing in this talk. So we'll not consider any test, but we'll focus on two particular tests. In the sequel, then we'll say something that is general for any test, but at first we focus on two tests. Okay, so first you see that as announced, I will really go standard and assume multinormality for the observations in my random sample x1, x2, xn. Then we look at two tests. The likelihood ratio test for the considered problem. And this has the form that you have there. So it's based on a statistic, on a test statistics QA, and this test statistics QA leads to rejection of the null hypothesis when you exceed the alpha upper quantile of the chi-square p-1, because indeed the null turns out that this QA is simply asymptotically chi-square with p-1 degree of freedom. Okay. And indeed, another null you would typically expect a small value of this QA, because under the null, this theta 1 0 will be closed from the estimate of theta 1, and of course then this theta 1 hat is orthogonal to all remaining eigenvectors theta j, and so you will have an inner product, this primes of the transpose there, you will have an inner product that is small under the null, so that it makes sense to reject under large values. This is really the textbook test, the one you will find in particular in the Anderson textbook on multivariate statistics. This is one test. Then I get another test, more recent test, which is actually essentially the Rao score test for the considered problem. It's based on another statistic, but this other statistic, which I will denote as QLC in the sequel, because turns out that this test has some optimality properties in the Lacan sense. I will not enter details, at least at this stage. But you see that this alternative QLC statistic is also under the null. It seems asymptotically distributed as a chi-square p-1, and you reject for large values of QLC again, with essentially the same intuition that under the null, this will be essentially close to S theta 1 hat, and of course theta 1 hat is an eigenvector of S, so this will be proportional now to theta 1 hat, and then you should end up with orthogonality with respect to the other eigenvectors, sample eigenvectors that you have there. Okay. So what I'd like to say at this point is that these two tests, they are essentially considered equivalent in the standard asymptotic setup. So what I will call the standard asymptotic setup is the asymptotic setup where, okay, of course, the sample size goes to infinity, but then the lambda j's are fixed. Everything is fixed. So this xi's just keep this Gaussian distribution with a fixed location mu, and more importantly, with a fixed covariance matrix sigma, in particular with fixed eigenvalues lambda 1, lambda 2, lambda p. In this asymptotic scenario, you really have that QA is equal to QLC plus something that goes to 0 in probability under the null. So that under the null, at least, those two tests are perfectly equivalent. In particular, they will show the same asymptotic size under the null. But from contiguity, this asymptotic equivalence will also extend to local alternatives, maybe not to fixed alternatives, but at least to local alternatives. Under local alternatives, you will have this same equivalence in probability between both tests, so that they will show the same asymptotic powers under local alternatives. So really, those two tests, they are in this sense equivalent under standard conditions. And so one motivation for this work was to, at least one early questions we had in this work was, does this equivalence between both tests extend to this setup where we have weak identifiability? So to be able to answer this question, we need to introduce this asymptotic scenario where you have weak identifiability. So now I have kind of a triangular array of random samples. Everything is indexed by n because mu n will be indexed by n, and more importantly, sigma n will be indexed by n. That mu n is indexed by n is really only for the show there, because both these tests are based on S, are based on the covariance matrix, and the covariance matrix, of course, is invariant under translations of my observations. So those two tests, they will be completely insensitive to the fact that I have various different values of mu there, which actually allow me to even restrict to a fixed value of mu, say, to make it simple, restrict to centered observations. Of course, it's much more sensitive what happens with sigma n in PCA, and for sigma n, I will adopt the structure that is there. So maybe I rewrite the sigma n in this way, because this is the expression of sigma n that emphasizes what are the eigenvalues and eigenvectors of sigma n. So you see, it's kind of a very simple setup where you would only have two different eigenvalues. You have a leading eigenvalue, which is this one. It is larger than the second one, but the second one, third one, and last and piece one are equal to each other. So you have kind of a subspherical setup where you have only one leading direction that is relevant, and all other directions are exchangeable, essentially. Okay, so the corresponding eigenvectors are θ1, our parameter of interest, and then the next ones are not identified. The next ones are in the orthogonal complement of θ1. Okay, are unidentified, but we don't care, because the only parameter of interest in our testing problem is this θ1, and that one is perfectly well identified as soon as lambda 1 is larger than lambda 2 and so on. So what we'll require is that this guy is different from 0, so that indeed lambda 1 is strictly larger than the other quantities. And so for the same, because of this invariance again, I will be allowed to assume that those common scales, sigma squared n, they are fixed, and I will fix them then to simply 1. This is again due to the fact that if I multiply all observations by a common factor, say I multiply all of them by 25, then it's an easy exercise to see that QA remains unchanged, and QLC also remains unchanged, so that I can always fix the overall scale of the observation. So if I fix mu n, and if I fix sigma n, then everything is parameterized by three things. My parameter of interest, θ1 there, and then this Rn and V. And you see that Rn and V is what decides about weak identifiability. If Rn V is small, where is it? It's over there. So if Rn V is small, then lambda n1 is close to lambda n, the other lambda n else, and I'm in a weak identifiability situation, so that V is fixed. So that it's really the Rn sequence that will decide how severe is my weak identifiability in the problem. If Rn is small, then it's severely weakly identified. If Rn is large, it's not so severe. If Rn is even fixed, so if I take Rn, which is 1 all along, if Rn is fixed, then I'm in the very standard setup where lambda 1 and the lambda else they are fixed, and this is the setup where where I know that both tests are perfectly equivalent. So in the sequel, my main interest will be in the case where Rn is a little over 1, Rn goes to 0, and let's see what happens in this very setup. Okay, so I start with results under the null, and under the null, here is the first result. The result is about the LC test, the second test, the raw score test. And the result says, okay, what's happening there is insensitive to the behavior of Rn. So this covers both cases that I had there. Rn might be fixed, or it might go to 0. Well, both cases are covered there. Rn is bounded there. So under the null, and you see that this is indeed the null because I consider as a fixed value of the first eigenvector, it's null value θ1, 0. Under the null, I have the asymptotic distribution that I had in the standard case where Rn was simply fixed. So I may here let Rn go to 0 even at an arbitrary rate. I will maintain this chi-square p-1 distribution, which means that my test will remain valid in the sense that its asymptotic null size will remain alpha even under weak identifiability. So I'm tempted to say that this test is robust than to weak identifiability, at least under the null hypothesis. And so this is something that you can check through simulations. So these are simulations under the null. You see that I take there a covariance matrix that is quite in line with the one that I had in my asymptotic scenario. So you have this θ1, 0 as a main eigenvector, and then you have the orthogonal complement for the orthogonal space, eigenspace, and then you see that the eigenvalues, they are 1 for the remaining eigenvalues, and something which is close to 1 for the leading one. And you see that the larger L there, the closer the first eigenvalue to the next ones, so the more severe the weak identifiability. Okay, so the more I go to the right in those two plots, the more severe this weak identifiability issue. And you see that in both plots, this is obviously reporting null rejection. So rejection frequencies of the LC test under the null. This is the LC test so far. You see that you are close to the 5% target nominal level for the small sample size, for this huge sample size. In both cases, you do well. And now we are tempted to say, okay, what's happening now with this other test, with the textbook Anderson test? And here is what it does for this moderate sample size 200. So it starts well, but this is a standard case where we know that the asymptotic distribution is indeed chi-square p-1. So far, so good. But it seems that this test is not robust to weak identifiability, and in particular for severe weak identifiability, you see that you achieve an empirical size under the null, which is about 90%, although you are conducting the test at 5% nominal level in principle. Okay? But you might say, okay, this is not so good for this Anderson test, but maybe this is a small sample issue. Maybe if you go to a larger sample size, maybe this will improve. And so, of course, you want to redo the same simulations for this huge sample size. And this is what you get. What you get essentially is that, of course, it's perfect in the standard case, and it's also very good in these two kind of setups where you have mild weak identifiability. But if you are more severe weak identifiability that it seems that even though the sample size is huge, this test does not do the job, and it totally collapses even under the null. It fails maintaining, it fails meeting even asymptotically the nominal level constraint. And basically what you see there is a theorem. That is, this phi A will not be robust to weak identifiability under the null, but it will be under those standard regime 1 and then not so severe weakly identifiable setup. So indeed, this is what we could prove. So in those two green regimes, 1 and 2 that you see there, indeed, so if Rn is either bounded, fixed, so this is a standard case with fixed eigenvalues, no weak identifiability, or if it goes to 0, so weak identifiability, but too fast to 0, so that the weak identifiability is not too severe, then you maintain the same asymptotic null distribution. So far, so good. Robustness to weak identifiability, provided that weak identifiability is not too severe. But when it's more severe, which were the case 3 and 4, in which over there the things seem to be so bad, then indeed you can derive the asymptotic distribution, which is a bit complicated, but it's still explicit there. And you can check really theoretically indeed the nominal the asymptotic size in those regimes under the null are not alpha. So this is Rn going to 0 at the same rate as 1 divided by root n, or even faster. Again, these are complicated distributions. There is just one case where it's a standard distribution. It's the case where you would actually focus on dimension 2. So you just have 2 eigenvectors. And we are in this most severe identified case. Then QA, you see, is asymptotically 4 times chi-square p minus 1. That is 4 times chi-square 1. So it's kind of nice, maybe, that depending on the amount of weak identifiability, you go from a QA statistic that is chi-square 1 asymptotically to a statistic, the same statistic that is now 4 times chi-square 1 asymptotically. It's a bit strange that such a thing happens, but actually it does materialize in the simulations. So here it's the same else as before, so no identifiability, mild weak identifiability, or fully severe weak identifiability. And these are histograms of the QA statistic. You see that at the very beginning of the story, what are those blue and orange lines? These are the PDFs of the chi-square 1 distribution and of the 4 times chi-square 1 distribution. So you see that at the beginning you have a perfect fit with the chi-square 1 distribution, whereas at the end of the story you have a perfect fit now with the 4 times chi-square 1 distribution, which kinds of confirms the previous theoretical results. With again awfully severe consequences in practice, because in practice you think in this last case that you are performing the test at 5% nominal level, but actually in this case the empirical size under the null is as large as 32%. So this is a test that you should forget about. So that's what we will do. We'll forget about it. tick on the next one then. Okay, let me skip this. What about the alternatives? What about power? So one test died now, which is this Anderson test, unfortunately, but we are still left with this Le Cam test. At least this guy resists weak identifiability, even if it's arbitrarily severe weak identifiability. But of course, the question is now, is this nice robustness thing obtained at the expense of power? It's of course very easy to define a test that will be robust under weak identifiability for arbitrarily severe weak identifiability. Just flip a coin, and this test will corresponding test will be robust to anything in the world. But of course, it will also not show any power. So it's important that we do results under the alternative to show that hopefully this phi LC test that is still alive will show power under alternatives. So this is what we did. And so now we have further results where we do not look at the null value θ1, 0 for our leading eigenvector θ1, but at the perturbation of it, so that indeed we are now under the alternative. And under such local alternatives, so these are local alternatives because there you have, so this τn is fixed. This τn goes to tau, so it's asymptotically, at least it's a constant. But this constant there in the perturbation is divided by root n times Rn, and this root n times Rn, you see in both cases there is going to infinity, so you divide by something which goes to infinity. So indeed you have asymptotically zero perturbation of your null value θ1, 0. So these are really alternatives that are local in the sense that they are shrinking to the null value θ1, 0. And this is usually what you need to do in the standard setup to get a non-trivial asymptotic power. And indeed you see that in the usual setup, which is a setup where the eigenvalues would be fixed, well, these local alternatives that you have there, they are of the form θ1, 0 plus a constant divided by root n, and this root n is the usual rate for local alternatives that you will be able to detect even for the student location test in dimension 1. This is the standard rate for parametric alternatives. So at this rate, in the fixed eigenvalue case, which is case 1, this chi-square p minus 1 distribution under the null is now becoming a non-central chi-square p with a non-centrality parameter, which is non-zero, and that will bring the power of the test. But actually, you have the same non-centrality parameter, essentially, or related non-centrality, at least you have a non-zero non-centrality parameter, also in case 2. And case 2 is this mild weak identifiability case. So even under weak identifiability, well, we have a non-central chi-square, so we have some power there. What will change under this weak identifiability case, weakly identified case, is that this rate root n for which we are able to detect those local alternatives will be modified and divided by root n Rn. So Rn is going to 0, so this means that, and this is of course very reasonable, this means that the alternatives that you will be able to detect asymptotically are more severe than the ones that you are able to detect in the standard case. So you need to go further away from the null hypothesis to get non-standard, to get non-trivial asymptotic powers. Okay, to get asymptotic powers that are larger than the nominal level alpha, which makes sense. You need to go further away to see the alternatives because the problem is more challenging. So you need more severe alternatives to see them. The problem is more challenging due to the weak identifiability that you included in the model. So this is, I think this makes some sense. So this is one, and case two, regime one. And regime two, of course, one may wonder what happens for regime 3 and regime 4 corresponding to more severe weak identifiability. Well, let me start with regime 4. Regime 4 is about this so severe amount of weak identifiability. Rn goes to 0 faster than 1 divided by root n. There, we have a negative result. We have a result that says that even if I look at those most severe alternatives I can consider, these are indeed the most severe alternatives I can consider, right? Because theta 1 is a unit vector. We know that it's only the direction that is of interest for principal and directions, principal eigenvectors. So we work with unit vectors to determine the direction. So the domain of theta 1, the parametric space for theta 1, is the unit sphere in RP. And of course, if I have a unit sphere for my theta 1, say dimension 2, if I have my unit sphere for theta 1, maybe the null value is that one. This is my theta 1, 0. If I now want a deviation from my theta 1, 0 to generate a perturbed value belonging to the alternative, I can consider local alternatives, and then this will provide me a sequence of theta 1 that goes to theta 1, 0. But the worst I can have as an alternative is a fixed alternative of this form. So theta 1, 0 plus a fixed location tau c. I cannot have more severe alternatives. I mean, I cannot have alternatives that would be of the form theta 1, 0 plus, say, nu n times tau n, again with a tau n that is fixed asymptotically, but with this guy that would go to infinity. No, to make it even more severe alternative. I mean, no, I cannot do that. Otherwise, I would get out of the sphere, and I cannot get out of the sphere for an eigen direction. So these are the most severe alternative I can work with. And the bad news is that for these most severe alternative I can work with, my asymptotic distribution under the alternative remains the central chi-square p minus 1. This is the same asymptotic distribution as under the null. Corollary, no asymptotic power. I mean asymptotic power alpha. So these are too challenging. This is a too challenging setup. Even the worst alternative I cannot detect. And you have something intermediate in case 3. In case 3, the most severe alternatives, you see again, you get the most severe alternatives I can consider. You need to go to the most severe alternatives to get some power. You have there a non-central chi-square p minus 1, but at least you have a non-zero, a non-centrality parameter. Right? My time is running out, so let me skip this part and just say a few words to summarize what we could get in terms of optimality. So there you have a negative result and this result. And one might wonder, is there a test? We looked at 2 tests. Maybe there is a 3rd test that actually will be able to spot alternatives in this challenging setup. And even maybe even in this case, you might have a test that will see less severe alternatives, or that will see the same alternatives, but under these alternatives that will show even higher power than this LC test. And indeed, we have kind of answers to those questions. Answers to those questions are related to the fact that the models there are quite regular in the sense that they are locally asymptotically normal. So they will show a log likelihood ratio for these local perturbations I was considering in the previous slides. They will show a likelihood ratio that is the same as the one you would get in a location Gaussian model up to a little p of 1 thing. And it turns out that when the model is so regular, then you know the form of the optimal test. You can really derive the optimal test. And it turns out that the optimal test that you can derive is actually asymptotically equivalent to this LC test. So at least in case 1 and in case 2, the QLC test is the optimal test in the asymptotic model we consider there. So for mild weak identifiability, this is the best guy you may actually consider. And for the remaining case 3 and 4, well, actually for 4, we have a result that turns negative result that we had saying that we get no power actually in this challenging case for the LC test. We have now a result that turns this negative result in a positive one, because the result there, what it says is that actually there is no way to discriminate between the probability in the numerator, the one in the alternative, and the probability in the denominator, the one in the null hypothesis. There is no way actually to discriminate between both the two probability measures. They are simply too close to each other. So that, okay, the LC test is not showing power against those alternatives, even the most challenging one in this challenging setup, but actually no tests. You can be as clever as you wish, you'll not be able to define a test that will actually show power for those challenging alternatives. It's just the nature of this regime that it's not possible to discriminate between the null and the alternative there. We have also, even it's more complicated, I will not enter details, kind of an optimality, a local optimality result in this kind of threshold regime 3 there. So I'm having 852 for me. So, okay, so if I want to, okay. So maybe one word about the real data example. I just shortly come back to the real data example, then I wrap up so that we have time for questions. So coming back to our real data example, Fleury was refraining from interpreting the theta 2 hat vector, although it was tempting to say that actually it's an aggregate between N and R, and that B and T would not contribute to what theta 2 actually is. So that is that what you want to test is that those two first loadings are equal, and that the next two ones are simply not there, which is what you see there. Okay, and then you make it a unit vector by dividing by square root of 2. Actually, what turns out is that when you apply your two tests, you have that the LC test has a p-value of 0.177, and the Anderson test has a p-value of 0.099. And I swear this is not cheating. This is really what the p-value is. So now I will claim that at 10% level in particular, you would reject. This is incredible, but it's what it is for this data. So now, since our results show that phi A under weak identifiability has a strong tendency to over-reject the null hypothesis when the null hypothesis actually holds, this we think is a strong evidence, at least strong hint say, that the null hypothesis should not be rejected in this case, right? And indeed, this is what you get when you perform some kind of linear node analysis. So you have that phi A is rejecting or borderline rejecting, whereas phi LC is, on the contrary, very often suggesting not to reject the null hypothesis. Again, in line with our results, we think that the proper decision in this case is not to reject the null hypothesis. Okay, I skipped the extensions. I'm sorry for being so slow. And I conclude with a quick wrap-up. Quick wrap-up is that we think that the main point in this paper is to show that weak identifiability is something that should not be neglected because it may hurt, it may turn a test that has in principle 5% level asymptotic null size say, into a test that has basically 0.95 asymptotic null size. So this may make your test completely useless. So one should be aware of this danger associated with weak identifiability. But the good news is that some tests turned out to be robust, both under the null and under the alternative to this possible issue. So that robustness indeed to this new thing, or I'm not sure it's a new thing, but robustness to this issue, say, should be taken into account. So high-dimensional cases on the agenda, although I confess that it seems to be awfully difficult, and this is no surprise because we know that in high dimension there are complicated regimes where it's not even possible to consistently estimate the eigenvalues. So this will be kind of tough there. Another thing is that we have now 1 or 2 papers where we have a similar story related to weak identifiability. It would be nice to have kind of a general paper where we have kind of a message that how score tests actually turn out to be the general framework robust to such issue, whereas on the contrary, val tests are not robust to such things. And again, this is joint work with Thomas Verdebout and Julien Rémy. These are the references. Okay, so thank you very much for your attention and for having me this afternoon.
Thanks, Davy. That was a great presentation and really good results. Would anyone like to ask a question or make a comment? Pierre?
Yeah. Hi.
Hi.
Can you hear me?
I can, yes.
Yeah. All right. So yeah, I'm Pierre. I'm working in the same school as Boris and Jerry. So I have two questions. So thank you for the talk. Indeed, very interesting. So my first question is a bit naive. Maybe it's in one of the first slides you divide by lambda 1 minus lambda 2, and you explain that the variance is kind of exploding. So I was wondering if this has any kind of relationship with the VIF in linear regression, this variance inflation factor. So that's my first question. And the second question is about if all these results have some implications in a context where you look at ICA, independent component analysis. I think you have some expertise in that already. Yeah. Thank you.
Thank you. So for the first question, I'm not really able to answer because I'm not so sure what is VIF, what is the variance inflation factor. So, but if this is a standard thing in linear regression, so maybe maybe you can describe it, but otherwise, I fear I cannot comment. This is related to some things in linear regression.
Yes. It's when you have two predictors that are highly correlated.
Okay. So
and then there is a formula a bit similar to the one you presented that express the variance of the beta hat in the linear regression. Yeah. And you can see on this formula that multicollinearity impact the variance.
So this is strongly related. So it's clear that you have variances blowing up when you have multicollinearity. You will start inverting non-invertible matrices and so on. And if you are borderline to such Okay, so you will have the exact same framework as here, that things are weakly identified, and by the way, it's even the same terminology makes sense, huh? Because under multicollinearity, under perfect multicollinearity, the coefficients are not identified. If you are under a strong, say, almost perfect multicollinearity, they will be then weakly identified. And the same thing happens. So inflation, arbitrarily large inflation of the covariance matrix, and correspondingly the information, the Fisher information matrix that will, on the contrary, go to zero. So this is indeed a perfect, and thanks for that, because actually I had not thought about this this framework. So
there is a R function called VIF or something. So
okay,
yeah.
Cool. Another thing in linear regression is such a thing called instrumental regression. You know, IV regression that they like much in econometrics, where they use instruments to correct for the fact that some variables are endogenous rather than exogenous. And there is actually literature about weak instruments. Instruments are supposed to be correlated with the covariates that are available in the data set, and actually maybe they are weakly correlated. They are correlated, but they work in asymptotic scenarios where the correlation with the covariates is actually shrinking to zero at some rate. So this is also something in linear regression that is similar to what we have here. For your second question, I'm sorry, I forgot your second question. Actually.
Yeah. It was about the potential relationship of your results to ICA, independent component analysis. Yes.
So I'm convinced that this has some strong counterpart in independent component analysis. So indeed, I have some paper about that. It's a long time ago, but by now, indeed, the asymptotic distribution of the standard estimator, such as FOBI and so on in ICA, they are completely well known, and the standard asymptotic results assume that the equivalent of the lambda i's, so say the quote-unquote eigenvalues for ICA, they are fixed and pairwise different. So same story, I would say. It would make sense to look at what happens where those things are not well separated, but when they get close to each other. This is a perfectly valid research question, I would say. Thanks so much.
Yeah, and I guess maybe also in the PLS, partial least square regression, there would be some sort of which. Yeah, it's used when you have a multicollinearity usually. It's a bit similar. There is a closeness between PLS and PCA. So
okay.
Maybe, yeah. Thank you for your answer.
Thank you for the comments.
Thanks, Pierre, for the question. Anyone else want to comment, or this is Spiro?
Maybe I want to ask, you started with some very basic assumption, and you at some point you said that you are assuming multivariate normality. I got lost later. Is it holding all across, or can you avoid it and things like that?
Yeah. So indeed, so everything I covered in the talk today strictly assume multinormality, but even in the first paper we relied that to elliptical distributions with finite force order moments. So all T distributions with degrees freedom strictly above 4 would be there, or lighter tails would be there. So and then we have the second paper where we actually have elliptical distributions, but without any moment conditions. So I would say ellipticity is the distributional framework we eventually worked with. Normality is not needed. So these results are not, I would say, Gaussian accidents. They are really related to the fact that parameters of interest become non-identified. Yeah.
Yeah, okay, thank you.
Jerry.
Hey, Jerry.
Hey, Davy, how are you?
Fine. What about you, Jerry?
Yeah, I'm good. Thank you for giving us a talk like this morning, quite early for you. So it's been a long time. I've tried to have you to give a seminar here. Always been reluctant to fly 24 hours. So it's good. For that, it's good. The pandemic, good science at least. So not anyhow, now I have a question. The world theoretical framework, like your alternative hypothesis, is based on that coefficient Rn, which tends to 0. So you assume you have θ1 is what it is, and then the other direction, or θ1 times 1 plus Rn, and this is how you define your weak identifiability, right? And so you assume that all the other eigenvalues are the same. So you have λ1, which stands out, and then you have all the others are equal.
Yeah.
Is that correct?
That's totally correct.
Yeah. So I was wondering if that has any influence on your results, like the fact that all the other eigenvalues or eigendirections are not identifiable, or if it would be in this case if you had, only one of those eigenvalue which is potentially annoying, rather than all of them together.
So it's a good point, and your intuition is totally correct. So the thing that you see there, maybe you don't see it anymore, but now you see it. So actually, you can redo this exercise, and in the setup that you suggest. The setup that you suggest is then to not have all those equal to each other, but only a few of them would be close to this guy, and the remaining ones would be now well separated from the first ones. And actually, it has quite a strong impact on the results. So this is, in some sense, really the worst case. And the worst case brings you there. And maybe if you have only half of the remaining values that would be close to the first one, and the rest well separated, you would be somehow there. So you suffer, but you suffer less. This is in some sense really the most negative case. So your intuition is fully correct, and we have not, at least so far, a general asymptotic analysis in this respect that would really measure the impact, that would quantify the impact of the number of conflicting, say, eigenvalues on those asymptotic powers or asymptotic rejection frequencies. So that would be of interest. It's actually, it's kind of, it's a complicated problem to have a general expression there too. So
Okay.
Our excuse in the paper was that, this is the most simple case you can think of. If things crash there, it's kind of, striking. Poor excuse.
Okay, thank you.
Good intuition, Jerry.
All right. Well, thanks everyone for the questions, and thanks Davy for getting up early and I guess great early on a Friday. That was a great talk. So I guess everyone is virtually saying thanks and clapping their hands. And maybe we'll get to have you, Davy, come to Sydney one day.
I would love doing that, despite what Jerry is reporting. So let me fly 24 hours as soon as this is again allowed. That is in 5 years from now, I think. But hopefully soon. Thank you
We
for
will
having me.
remember.
Thank you, guys.
Thanks a lot.
Ouais. Il va juste me manquer de boire une bière après le séminaire, quoi.